Hi, in this video, we want to take a look at improving our linear models using the log transform. All right, so the big idea for this video is that we have our data, we're looking at our data, and it looks like the residuals do not have constant variance. All right, why is constant variance important? Well, if I want the line of best fit, that's really a feature of geometry. That's not actually an aspect of statistics and probability. So the line of best fit is always the line of best fit. But as I start like getting deeper into regression, I'm going to want to do hypothesis testing, because hypothesis testing helps me establish inferences about the model, about the data, stuff like that. Well, so I'm looking at the data and I see I do not have constant residuals as so if you change a predictor value and you see that you have a change in variance on residuals, then you cannot trust your p-values when you run hypothesis testing. Okay, well, if I can't trust my p-values, then I can't do hypothesis testing, period. Now, I could still use the model itself if I want to, because that's from geometry, not statistics. But usually, if you have that situation where one of your hypotheses are not holding together, then you don't have as good of a model as you could possibly get. So what we want to do is we want to somehow improve our model and make it a better model. Well, one option that we have is that we can use a log transform. So remember, logarithms from college algebra take non-negative values, so positive, sorry, it's not non-negative, it's just positive values. They can't be zero, and they convert the integer part is going to be the exponent from scientific notation if we're doing base 10. Now, natural log is what we're actually going to use, but it's a similar concept that logarithms convert numbers to the magnitude of the number. All right. Now, there's two major transforms that we typically look to, the two big ones. First one is the square root transform. It's in another video, and the log transform. All right, so let's go ahead and start looking at the code. So for this example, we're going to go ahead and use the Confood dataset, Confood 1 from the textbooks website. And so when you take the file, it has a header, so I have to put header equals true. Remember, I always recommend that you use a file path and load your data using code. Use something like file.table, file.csv, something like that. It'll make it a lot easier in your projects. If you're clicking in RStudio, it's gonna bite you in the backside. All right, so something that is not in the textbook that I always do is that I color my all the scatter I color all the points with in a manner that corresponds to our target variable. So this part of the code, what I'm doing is I'm getting a color palette going. I'm just saying, hey, I need colors from the Veridis package, and I'm saying, okay, I want to have as many colors as I have data points, so I go ahead and say n is equal to the number of rows in the data set. And so that just gives me the colors. Now, the colors are not in the correct order at this point, because I want the colors to correspond to the values of the target variable. So what I have to do, I have to take the order of the target variable, which is sales in this situation. We have price and sales in this data set. Price is our predictor, sales is our target variable. And then what I do an inverse permutation on the order, because I can treat the order as a permutation from abstract algebra, from combinatorics, from you may have seen it if you took liberal arts mathematics, maybe, hopefully. And then what I do, this inverse permutation gives me the index sequence to be able to rearrange the color vector. And then I go ahead and put that into the data frame so I can use it repeatedly. And so as I set this up, dark colors will be the lesser values of the target variable, and the bright yellow colors will be the greater values of the target variable. And that can really help like make some features pop out when we start looking at our plots. All right, so let's go ahead and build our vanilla regression model. So now as I go through this, I'm trying to write this code in a manner that's similar to how I actually go through and analyze data and make my own personal decisions. The main difference in these examples I have in these videos is that I'm really only using one technique at a time. I don't use a collection of techniques. I might have to like omit variables, and I might have to use a square root transform on one predictor and a log transform on another. I might have to do some other things. There's a lot of things we can do to get to improve our linear models, but in my videos I'm just showing really one technique at a time. So in our vanilla regression, we're saying that price, which is something that we have control over, is going to have direct input into how our sales go. Okay. So let's take a look at the model that we get. And I'm like, wow, these are kind of big residuals. Those are big residuals. But I can see that my coefficients are highly statistically significant, very small p-values. And I can see that the f-test is statistically significant, but my r-squares are awful. I mean, 0.4 both times. Well, at least these are close. That means I'm not overfitting, or it doesn't mean I'm not overfitting. That just gives me confidence that I'm not overfitting. All right, well, what I want to do, I want to start plotting. I want to make a good solid scatter plot. I want to get my prediction interval to see how does my prediction interval compare to my observed data. If I see a bunch of points outside my prediction interval, it might be that I have some problems with my assumptions. So to get my prediction interval, I build a score data set. Remember, a score data set is the data set that I predict on. So what I'm doing, I'm taking the price range of values. So I take the minimum price in the data set, the maximum price, and if you look at the data, everything is at the 0.01 like increments. So I go ahead and just go through the sequence of values from the minimum to the maximum, and I'm increasing by 0.01 for each value. And then I store this in a data frame, because when we use when we go to drop this into the model, it needs to be a data frame. When I set new data equals score, score needs to be in a data frame format. Now, something about R is you have to have the right format when you put it into a function for it to work, which can be kind of frustrating. Most of the time, if it's a data frame, you're probably in a good state. It's not 100% guaranteed. This is actually why I don't use a lot of the more recent formats like Tibbles that come out. The tidyverse. I usually don't use tidyverse formats of data, because in a lot of the older functions won't accept like those more exotic formats, but all the newer functions will accept the older format. So I always keep things in the older format so I don't have to fight with it. All right, so what I'm going to do, I'm going to run a prediction interval, and it's going to give me the fit value. It's going to give me upper and lower of the prediction interval for each value of the predictor, for each value of price. And you'll notice that I store it in a data frame. Now, one thing that came up when I was looking at this was that this is going to give me negative lower bounds, and it actually gives me a few negative fit values. So what I did was, well, if I'm talking about sales, does it make sense to have negative sales? No, it doesn't. So I go ahead and I replace those values with 0, because I want my model to make sense. I need a model that makes sense. If I show negative values, again, I present this and they go like, negative sales doesn't make sense. You're an idiot. It takes away my credibility. Ultimately, something that is very important when we do data science is that our job is to communicate. Our job is to communicate. That's really what we are doing. So you always need to think about who is your audience. If you have to explain your model and you have negative values and the person goes, well, that's just stupid, you have lost the ability to communicate with that person. So you always want to focus on what will make your audience receive your models, receive your work better. A simpler model that is well received is far better than a slick, advanced, theoretically correct model that will not be accepted. All right, now I'm going to go ahead and build scatter plots, or just one scatter plot. So this just tells R to put, they only have like one plot. I could put subplots if I wanted, but I just put one in here. And then I do a scatter plot. You'll notice I'm using the color that I defined, col equals the color. And I'm using point character or plot character 19. That's a solid dot. And then I'm taking that, the output of the predict function. I put the fit, the lower bound, and the upper bound, and I make them red and I just plot them. So that this is putting down the 95% prediction interval. And let's take a look at what comes out. Okay, well, I'm looking at this and that point is like really high up there. And something that jumps out at me when I look at this, I have points above, points below, and then points above. So, you know, like, yeah, that is the line of best fit, but I can see that I've got a bunch of points above, in the middle they're below, and then on the right they're above my line of best fit. So I'm kind of worried about this. We don't want to see a pattern when we look at our residuals, and I kind of see like a U-shaped in my residuals. So what I'm going to do is I'm going to go ahead and plot the linear model. And what I'm going to do, so remember, R has 4 default plots. If I want all 6, the ones that involve Cook's distance, I need to go ahead and say which equals 1 through 6. And I'm using color to try and be able to like grab an additional inference on what's going on. Okay, so remember, fitted value is going to be pretty close to the observed value, and the observed value corresponds to color. So seeing a pattern in the color is okay on this one. Now this 38, that now I went through and I looked through the data. That's that one that was, that point that was really off. Okay, I'm looking at my normal QQ plot. Well, that point is pretty far off. It's kind of weird to see a bump in here. That's kind of atypical. And on this scale, with this point so high up, it's hard to tell if I've got something going on over here because things are not zoomed in correctly. Remember, I don't want to see like a bunch on the mainly focus on the far left and the far right of the normal QQ plot. If I see like points going underneath on the far right, I see them going underneath the line or above the line. That's a problem. If I see on the far left points going underneath or above the line in kind of a systematic way, then that's when I start getting worried about the normal residual assumption. Scale location at this point, I mean, this is a big gap, but you know, between this point and everything else. Our Cook's distance, once again, that 38 is definitely interesting. And residuals versus leverage. And you can see like the same points come up over and over and over. Now, so something that's going on is that because of the scale of these visualizations, the 38 is like really pulling it off. It's hard for me to really see what's going on. All right, so what we're going to do, we're going to transform our data using the log transform. All right, so in our regular log is not base 10. When you see like a scientific calculator or graphing calculator and you see log, that means base 10. And it's all about that base, no trouble. So once you get into the math community, log means natural log, base E. E is that special number, has infinitely long decimal representation. It has a ton of properties. If you've taken calculus, you know this number well. If you haven't taken calculus, you really haven't worked with it. And so just to show you that it's the natural log, when I put 10 in, if this was base 10 log, I put 10 in, I should get 1. If you put the base in, I get 1 back. All right, so now here, exp of 1 is just E. I put that into log and I get 1. And here in R, I can change the base to any number I want. 10 is for scientific notation. So if I'm presenting to engineers or scientists, I might want to go base 10 because that's more natural for them. If I'm working on a project that involves like like I'm doing binary stuff, then I might be working base 2 because that's very natural for the project. All right, so how do we do this? We have 2 choices when we want to do our transformation. We can either manually transform the data or we can let R do the work. Now, manually transforming the data, you want to avoid that if you're going to have new data coming in. If I have a stream of data, I have to put it into the model and then go. New data comes in, put it into the model and go. And I have to keep on repeating. I probably want to just let R do the work for me. In that situation, I'm going to go ahead and put log into the formula itself. And that way I just drop it into R does the work, that's good. Now, if I'm in a situation where I'm only going to be running a model once, or I'm in like maybe a big data problem where I'm going to be trying a lot of different situations, a lot of different combinations, I'm experimenting around, I might want to go ahead and transform the data and store it on a data frame. And if you look at the textbook, that's how the author does it. Advantages and disadvantages both ways. I feel like for the students that are in my class, this is probably the best way for most situations, is to let R do the work, if you can. So I go ahead and put log in the formula. And now let's go ahead and take a look at the output. So now something that to remember, if I start seeing problems with my model and I have skew right data, or I see that's like financial data, frequently the log transform is the one to go with. So now here, this is a different scale of residuals, because now everything is on the log scale because sales is now log transformed. So this is the log of what I want. I have to take an exponential if I want to convert residuals back. So I can look here and I can see how big these are. If I think about the e to the power of 1.3, that's much smaller than the residuals I was getting in the previous model. That's a big improvement. Now here, the p-values are even smaller. They were small before, but now they're even smaller. So that's in the right direction. But the big one, the big change is see how much larger the R squares are? I mean, they were what, 0.4 before, now they're 0.67, 0.66. That's a huge change. That's a huge improvement. All right, well, now what I want to do is I want to go ahead and plot this. I'm going to plot both the model, the original model, and I'm going to plot the log transform model on the same scatter plot. And I'm going to use that to try and go, hey, which model is better? Which one should I go with? So what I'm going to do the predict like I just did before. But remember, this new model puts out everything on the log transform scale. So I need to undo the log transform. How do we undo it? We use the exponential function. So see right here, the exp. All right, so what I'm doing, I'm taking the predicted value, I'm taking the lower bounds and the upper bounds, and I'm putting them into the exponent of E, and then I'm transforming it, and that's going to be my predicted values. And so boom, it's easy peasy lemon squeezy. So now I'm going to go ahead and plot it. Now the plotting is the same as the previous scatter plot. If I was working on my own at work and I was not using R Markdown, I wouldn't repeat this part of code. I would just go ahead and put the upcoming code onto that part of the code I've just already built. And you'll see here, I'm going to plot it in blue, and I'm going to set line type to 2 so that it's dashed, so it makes it easier to see the difference in the two models. I'm going to put a legend on here. All right, so now, so this does get a little bit crowded, but let's take a look at this. You know, everything, so this middle blue line is my fitted values. This lower blue line is the lower bound of the 95% prediction interval. And this upper blue line is the 95% upper bound for the prediction interval. And all through here, I'm actually feeling pretty good about this. As I scoot down, going all the way up to about here, like they're pretty well centered. The line is going pretty well through the center of the data. This is an improvement from what I previously had. Now, when I go over here, I see that all the points are above. That does make me worry, but a good rule of thumb is if I could take 1 point and move it, if I can take 1 point and move it, and it would change my visual impression, then I probably don't have to worry about it. So if I was to pick up this point and move it down here to where it would be ideally, then visually I would feel a lot more comfortable with this. And so I'm going to go ahead and just say this is a good model. It may not be the best model, but I think this is pretty good for the amount of data we have. So let's look at the diagnostic plots. So now here, go ahead and just plot the standardized residuals. And, you know, so here we do have some up and down, a little bit heavier on the downside over here, and heavier on the positive side over here. But sometimes, you know, it can only get so good in the data. You know, the data is what the data is. All right, so let's see. Things looking pretty good. All right, so here I'm going to conclude that this is not normally distributed. So I have to be very cautious about using hypothesis testing on this. But overall, I feel like this is much better. See how much closer this is to everything else? It's not warping the entire scale like it was before. I would definitely want to take a look and see if there was something going on with 0.38. There's some anomaly that makes it so that I should not include that data point. Everything's just looking a lot better on this. Still big though. I did rerun this model without the 38th point, and it did perform a lot better, but I only wanted to keep one technique in this video for today. All right, well, that's all I got for you. Take care and goodbye.